Hey everyone, we're here for another lesson. This lesson is over section 4.5. Section 4.5 is going to be over dilations. So we got section 4.5 here. A dilation is a transformation in which a figure is enlarged or reduced with respect to a fixed point C, and that point is going to be the center of dilation. Usually that's always going to take place at the origin if it's on a coordinate plane. If it's just not on the coordinate plane, just out in space, we have a random point or fixed point C. Things are going to get larger. That a triangle, a rectangle, whatever polygon you have, it's going to get larger or smaller based off of a scale factor. We use the letter K to represent scale factor, just like we use M for slope or B for y-intercept. We designate scale factor as K. If the K value is bigger than 1, we're going to have enlargement. If the K value is between 0 and 1, we're going to have it reduced or reduction. Okay. The key thing here is that this is not rigid motion where the side lengths were constant and the angles were constant, as in they stayed congruent. This particular problem, or any type of dilation, the angles are maintained, they're preserved, they stay congruent. It's the side lengths though that are changing, so that's not rigid motion. Okay. Also, one thing we have to consider is we always take the image divided by the actual or the pre-image. So it's always image length divided by actual length or pre-image length, and that will give us K, which is our scale factor. First example, we want to find the scale factor of this dilation, tell whether the dilation is a reduction or enlargement. Again, we're going to take the image length divided by the pre-image length. For this case, it would be 12 over 8. The ratio of 12 to 8 would be the same as the ratio of 3 to 2. If you want to change that to a decimal, that's fine. That would be 1.5. So K is 1.5. That number is bigger than 1. And since K is bigger than 1, this problem is going to represent enlargement. So enlargement, again, we're going from a smaller safety pin to a larger safety pin. For the paper clips, you can see here we have P prime. It's getting closer to that fixed point C. This is going to involve reduction. Okay. My reduction, again, in this case, again, is going to be CP prime over CP. And CP prime, I'm sorry, will be 18. And CP will be 30. If we reduce that, we're going to reduce that down to 3/5. And 3/5 is in between 0 and 1. So K is our K value. Scale factor is 3/5. In this case, again, that represents reduction. So everything I'm writing down, you should be writing down in the notes. If you're just sitting here looking at this, that's good. You're observing, you're watching, you're listening, but I want a little bit of interaction and writing things down as well. You can write this down on graph paper or just regular white paper. So let me give you a second to do that again if I didn't clarify that. Expectation is that you write some things down before you get started with the assignment. Okay. Next one, we don't have a picture, but our principles of image over pre-image are going to be maintained. This particular case, we're going to take 3 over 12. That ratio is really our fractions 1/4. So K is a fourth. Since K is a fourth, that's going to represent reduction. Okay. Scale factor of fourth, reduction. For this one, anytime we're going to dilate on the coordinate plane, now we're going to dilate from the origin, or it's kind of originating. Getting larger or smaller comes from the origin. So from 0, 0. Real simply put, if K is bigger than 1, obviously we'll multiply our X and Y coordinates by that number, by that constant scale factor, or K. If our K value is a fraction or a decimal, we're still going to multiply X and Y times that scale factor. It's just if it's bigger than 1, we're having enlargement. If it's less than 1, we're having reduction. But you will multiply the X and Y coordinates by the scale factor. Let's just try a couple here. So first example, again, those lines are not straight. Bear with me here. Let's go A prime. Let's go B prime. Let's go C prime. And we're multiplying each coordinate by 2. So I'm going to get 4, 2, 8, 2, and 8 -2. Again, you should be doing this on graph paper. You should have already grabbed graph paper. If you haven't, hit pause, go ahead and grab some graph paper. I'm going to graph the original here though, so go ahead and hit pause. If you graph the original pre-image and image. Okay. I'll graph the pre-image a different color. So let's go with 2-1. Let's go with 4-1. Let's go with 4-1. Maintain our color here. 4-1. We're going to connect the dots and label A, B, C. I'm going to put my image in purple here. So we've got 4-2. We've got 8-2, 5, 6, 7, 8. So 8-2, and then 8-2. So we're going to go like this. Okay. Now, again, we're going to go A prime, B prime, C prime. Now, normally they do in the book. You see, if you look at these, they're going to put the new figure. Have it be dashed in terms of connecting the sides with a dash line. I'm okay if you don't. Understand that if I did do that, we would obviously just make that a little bit of a race. We'd have a dash line here. The reason why they do the dash line is just simply to kind of show more adding into, if we make this three-dimensional, and the fact that it just kind of makes it a little more distinct, that we have two different shapes, different sizes, and one of the connecting of the sides is solid and the other one is dashed. So usually it's always the image. The new one is the dash line. Okay. So basic there, a scale factor of 2 on that one. So one, you'll have to do that quite a bit. Okay, for next one, we're going to do some reduction. Scale factors a third. I usually just think divide by 3. It's fine to multiply by a third, but that's really the same as dividing by 3. So if we go ahead and do that, again, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Make it 6. Sorry, 6. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6. A little close there. I'm going to graph the image first. -3, 6, 0, 6, 3, 3, and -3, -3 here. Okay, connect your dots. Connect your dots. And our new one, let's change colors. Let's go K prime. Let's go L prime. And let's go M prime. And again, you should be graphing this as well with me. If I divide by 3, we're going to get -1, 2. We're going to get 0, 2. And we're going to get 1, 1. And then finally, don't forget N prime, -1, -1. So if I graph that, we'll have a point here, a point here, a point here, and a point here. And we will get this right here. And my labels, make sure we label here. So if I go back to red, I've got K, I've got my L, and I've got my M. Oops, sorry, missing one here. Missing my L, sorry. Back. Oh, sorry, it should look like this. Let me erase that. Erase that out. Put that back in. There we go. That looks better, a little bit better. Okay, and then finally N. Okay. Moving on. Labeling K prime, L prime, M prime, and N prime. Okay, so again, this figure is getting smaller. It's reducing. New side lengths are a third as long as the original, or we can say that the pre-image lengths are 3 times longer than the image points, or image length. Okay, so again, that's a perfect example of reduction from the origin. I'm going to give you a couple minutes to try 2 and 3 on your own. Go ahead and hit pause. Try these two. This one is a scale factor of 4. This one is a scale factor of 0.4. I'm fine with you leaving it 0.4 if you really want to change it to a fraction. So it's either times 0.4 or you could do times 2/5. I'm fine with either one of those, but we're going to have some reduction for the bottom one, enlargement for the top one. So go ahead and hit pause. Make sure you try 2 and 3. Okay, hopefully you've come back. A couple more examples. We have a triangle here. We want to apply a scale factor of -0.5, so we can graph its image. Only thing I want to point about the negative here is, yes, the half is going to make it reduced. The half will make it reduced here, but we also want to factor in this negative. What's happening is when you normally multiply x and y by negative, remember we have this as one of our rules. We multiply, our positives become negatives. That is rotating, and that is rotating 180 degrees. So this is going to be a rotation of 180 degrees, okay? And obviously reduction. This one's going to be reduction, okay? So again, if I graph the original, -1, -2, -3, -4, -2 will be down here. -2, 4 will be up here. And -2, -2 will be down here. So again, connect your dots, connect your dots, connect your dots. And we are going to really rotate and reduce. We're going to rotate and reduce. So I've got F, I've got G, and I've got H. Let's switch it up and go green. So I've got 1, 2, 3, 4. Again, let's come up with our new coordinates. So F, G, and H. Okay, again, we're going to multiply by half now, or -0.5, sorry, -0.5, which is going to make this one become a +2, and that one's a 1. This one's going to be a +1, and a -2, and this one is going to become a +1 and a +1. So 2, 1, 1, -2, and 1, 1. And again, if we connect the dots, we will get this. And again, label, so F prime, G prime, and H prime. So again, we're rotating 180, and we're reducing. Okay. 2 more. This time we're going to take a photo that was 4 by 4 inches, and we're going to, looks like, reduce it down to 1.1 inches. So 4 by 4 square to a 1 by 1 square. I'm going to reduce that down. So again, all we're going to do is take our image length divided by our actual or original, or I call it the pre-image length. So in this case, we're taking 1.1 divided by 4. You can divide that out. Really, we want to keep this as a fraction. I know decimals work, but this is going to become 11/40, and that will be our k value, and that's reduction. 11/40 can't be reduced. Just move your decimal over one place to the right. Okay, one more here. Again, we're going to take image over pre-image or actual. If I do that, we're going to say that the image length here says you're using a magnifying glass. It shows the image of the object that is 6 times the actual size. Determine the length of the image of the spider shown through the magnifying glass. Okay. So again, we want to magnify. We're blowing this up. The image length is x. The pre-image length is 1.5. Okay, so we have that right there. And that is going to equal to 6. So we know image over pre-image equals scale factor. So now if I want to solve for x, I can just multiply both sides by 1.5. I do that, I'm going to get x equals 9. Okay, so again, we're saying that the image length through the magnifying glass is 9 centimeters. So it's going to look 9 centimeters, but in reality, it's only 1.5 centimeters. But we're making it 6 times larger. There's a couple more examples. You can try them if you want. The assignment is on page 212 to 213, 3 to 6, 15 to 22, 24, 25, 28. Again, a lot of these things you will be graphing, so you do, again, need graph paper. We will be turning it in on Monday. Whatever you don't finish in class today, you'll need to finish outside of class. We're kind of reaching the end of the chapter here again, so I want to wrap this up with one more section after this, and obviously some review and getting towards another test. So again, the writing prompt, just asking you how are dilations alike / different from rigid. Dilations are alike because the angles are maintained. The angles stay the same, congruent, corresponding angles are congruent, but the side lengths are different lengths. And what makes something a rigid transformation is when the angles stay the same and the sides stay the same. So when you rotate, you reflect, you slide, that's rigid because everything is being maintained. Side lengths are being maintained, angles are being maintained. It's the same shape. It's just been moved to a different position, different location. But with the dilation, it is getting larger, smaller. So we're kind of talking about similar figures, not congruent figures. So that is not considered a rigid transformation. So again, there's your assignment. Make sure you copy that down. Please get started. Use your time wisely. Follow the rules, meet expectations, and we'll be checking everything on Monday.